Hey, for the past couple of days, we've been talking about these antiderivatives and are they unique. And from yesterday, we said if we know the derivative of a function, let's say is sine of x, we want to say, well, will this function be unique? And of course, why or why not? So we want to find the original function itself. And to do that, our rule said we have to use this antiderivative. We would get the antiderivative of sine of x dx. And our rule from our trig rules from yesterday said the antiderivative of sine of x is this negative cosine of x. But we have to add this plus c1, that constant of integration. And we want to say, well, will this be unique? And of course the answer is no, this is not unique. And because we don't know c. C could be anything. If I were to take the derivative of this function right here, the constant becomes 0. Remember, this sine of x, we're saying this is the derivative of our function. And because c could be any constant and the derivative of any constant is 0, we really don't know what this is. So therefore, c could be anything. So therefore, we say it is not unique. So today we're going to take a look at it as well. How can we make this unique? And that is how we solve for C1. To find the actual value for C1, we must know something called an initial condition. Knowing the initial condition, right here, can lead us to what we call the particular solution for an antiderivative, or our integral. The phrase integral and antiderivative, they're going to be synonymous with each other here. And so what we're going to talk about today is, well, how can we find c? So let's see. From the problem above, we want to find the particular solution. In other words, what they're asking us to do here is to find c1, find that constant of integration. Given the derivative is sine of x, and we know that the function goes through this point. This is what we call the initial condition. This is what we call a differential equation. A differential equation is any equation that has a derivative. And what I like that it says is that it's an equation. We want to solve this equation. So if we're given a derivative, we undo the derivative. It's like adding and subtracting. If I have x plus 3, if I know that x plus 3 is 7, I can solve addition by subtraction by doing the inverse operation. Well, what's the inverse of a derivative? It is an antiderivative. So let's see how we actually use this. From above, we know that the function f of x is this negative cosine of x plus c1. What we're going to do next is find c1. To do this, we're going to find out which function. Remember, this c1, it's telling us that there are many possibilities. In other words, there could be an infinite number of constants that will make this true, that will make this function work. But we only want the one that goes through pi 1. So what we're trying to do here is we are trying to find the equation, the function f of x, that only goes through the point pi 1. And I can solve that. This is my function. My x value is pi. My y value is 1. And I can just plug that in. Given my function, at the point pi 1, if I were to plug it in, my y value is 1, negative cosine of pi plus c1. Well, what's the cosine of pi but negative 1? So this is 1 equals negative times a negative 1 plus c1. So c1 just becomes 0 if we were to solve it. So what does that tell us? Well, that tells us what our function is now. F of x is negative cosine of x plus 0. And that is our function. I just plug it in. We just plug in. And this is the solution to the differential equation, we call it. In other words, it is the solution that has this derivative, it is the function that has this derivative, and goes through that point. So let's take a look at a bunch more examples here. We want to find a particular solution. In other words, this is saying solve the derivative equation that satisfies the initial condition f of 1 is 0 for our derivative f prime of x equals 1 over x squared. Now, when we solve these, there is a particular way we have to solve it. Step 1, we are going to write out what our function is equal to. To get the function, we are going to take the antiderivative. Whoops, that is terrible looking. The antiderivative. Now, 1 over x squared is just x to the negative 2, so I'm going to write it as x to the negative 2 dx. Don't forget the dx. Now, the AP is not going to tell you to do this. You have to write this. You have to remember to write this. Later on, I'll show you where it really comes from here. Taking the antiderivative, we would add 1 to our power. This becomes x to the negative 1 over negative 1 plus c1. So my function is the following. Negative 1 over x plus c1. There is my indefinite integral. Remember, this is not unique. So what we want to do is make it unique. We want to find the only function that has this derivative that goes to the point 1, 0. So now we are going to find c1. To do that, we're going to use the initial condition. My x value is 1, my y value is 0. And I can just plug it in. We would get 0 equals negative 1 over 1, because my x value is 1, plus c1. And what does c1 equal? Well, that's just going to become 1 for us right here. So my new equation, my particular solution, is going to be this. F of x is negative 1 over x plus, whoops, remember that was a 1 right there, plus c1, 1. This is our particular solution. Now, where this was not unique because we don't know what c1 is, this one is unique because we found c1. We found it. We know what it is. There's only one that goes through this equation. Now, we're going to talk a lot about this throughout the whole year, so if you're not getting it all yet, just make sure you do the process. This is a very big topic for us that we're going to see throughout the year. So let's try the next one, part number 2 here. Oh no! Find this particular solution that satisfies our particular solution that satisfies our initial condition. Q of 0 is negative 6. So they're saying when Q is negative 6, whoops, they're telling us that Q is negative 6, and the other variable is Z, and Z is 0. So when Z is 0, Q is negative 6. We want to solve it. So for this one, we're going to do a little bit more work than we have to, and I'll show you what we really need to do. We're saying dq dz equals negative 6z squared minus 3. We want to solve for q. So to do that, I'm going to multiply by dz. And I get this dq equals negative 6z squared minus 3 dz. Now remember what I told you. This is called a differential. They're not going to tell you to put it here like in the example for number 1. But notice over here, notice what do we have? We get this dz. It actually comes from solving a derivative. Now our next step is to solve the derivative itself. So what solves a derivative is the antiderivative. I want to undo the derivative, and that's what we're going to do here. We're going to undo the derivative. So to do that, we integrate both sides. This just becomes q equal to. It does have a plus c, but we're not going to worry about it. We'll talk about that later on. Here is our power rule. We're going to get negative. If I add 1, it becomes a 3. Divide this by 3, we get negative 2z cubed minus 3z plus c1. This does have a constant, but that is also a constant. We only have to write it down one time. So there is our, what we call the general solution. Actually, that's a name for it. It's called the general solution. And again, it is not unique. So what do we want to do now? We want to solve for C1. So we want to find C1. And they give us the condition, which we saw up here, when Q is negative 6, Z is 0. There's my condition. Remember, there are infinitely many functions that have this derivative. That plus C says there's many possibilities, but we only want the one that goes through this coordinate here. So I can just plug it in. Z is 0, Q is negative 6, so I'll go negative 6 equals, that's just 0, minus 0 plus C1, so C1 is just negative 6. And then I can just rewrite my answer, my general solution, my particular solution. Q is, that should be a C1. Let me rewrite that better. Q is negative 2z cubed minus 3z plus c, which is a minus 6 for us, so I'll go minus 6. And that is what we call the particular solution. All right, go to video number 2. We'll take a look at a few more examples. I'll see you then.